Okay, so today we're going to do some probability. This is one of the last things that we actually have to do in the entire course. This is the last component of our data analysis unit. Anyway, let's get going. So today's plan is going to be, we're going to introduce probability. We're going to look at bias samples and some assumptions with those bias samples. Then we're going to look at the real main thing today, which is the measures of central tendency. These are three different ways that we can measure the average of something. There's the classic way and there's two other ways. We'll get into that when we get into it. And then, of course, you'll have some practice time today. Anyway, let's get rolling. So first things first, probability is the likelihood of an event occurring. So this is going to be the main focus for the beginning of today. Probability is just calculated in its basic form as the number of successful outcomes divided by the total number of outcomes. So in other words, if you were to look at the probability of something happening, you'd look at the number of times that that happens out of the total number of times that could have happened in the first place. Now, there's two main types of probability. There's theoretical probability, which is the mathematical likelihood of something happening. This is usually just measured by saying it's the number of possibilities of what you think is a success divided by the total number of possibilities in general, but it really depends on a lot of context. Theoretical probability is a little bit more technical to find. Experimental probability is the one that's a lot easier to calculate, to be honest. Experimental probability is the actual observed likelihood of something happening. In other words, in order to have an experimental probability, as the name would suggest, you would need to have done an experiment already. So if you did an experiment, and let's say you did 20 trials, and out of those 20 trials, you saw that 2 of the trials were a success, then you would say the experimental probability is 2 successful trials out of total number of trials of 20, right? That would be your experimental probability. Now, your theoretical probability could have been something totally different, but it is what it is, right? So something may happen more often or less often than expected. It is all up to chance after all. Now, a good example of this, just in case you're hearing this and just going, what the heck, a theoretical probability, experimental probability, what on earth is the difference here? Well, imagine the simplest situation would be flipping a coin. When you flip a coin, it could be either heads or tails. And let's say heads just was, for the purpose of this, heads is a success, right? So if we said heads was the successful outcome, like that's the one you were betting on, then you would say that the theoretical probability is 1 successful outcome out of 2 outcomes in total. So that would be your theoretical probability. Now, if you did an experiment, though, let's say you flipped a coin, I don't know, 10 times, that would be your total number of outcomes would be 10. And let's say of those 10 times, it was only heads 3 times. Well, 3 out of 10 would be your experimental probability. If you were to do another experiment, it could be different, right? Your theoretical probability and your experimental probability are not necessarily the same thing. But again, it is what it is. Anyway, those are 2 different types of probability. You will need to know both. Oh, okay, perfect. Here's a coin being flipped example. We kind of already did this. So what is the theoretical probability of heads? Well, we already just kind of went into that, right? So we could say that the successful outcome is 1 out of 2 outcomes possible in total, either heads or tails. Now, in the past, every single year, actually, I think that I've taught this course, someone's always like, oh, what if the coin lands on its side like this? It's like, no, that's not going to really happen, right? So we're going to say 1 out of 2 is our theoretical probability. Now, what if the coin was flipped 10 times and landed heads 6 of those times? What is the experimental probability of heads? Well, in this case, since it landed heads 6 times, 6 successful outcomes out of 10 outcomes in total, so 6 out of 10. I didn't mention it before, but probabilities as fractions can always be reduced. This, of course, could be reduced by dividing by 2 on the top and the bottom, so that would give you 3 out of 5. So the experimental probability in that case would be 3 out of 5 rather than 1 out of 2. Anyway, moving on. So populations and samples. Probability can be used to make a prediction regarding a population given a sample. So in other words, if I give you a sample and you knew probabilities regarding that sample, you could extend it to a larger population just from a sample. This is really the whole crux of why we were only dealing with samples in the previous lessons from here. When I said sometimes you don't have to survey an entire population because there'd be too many people, for instance, this is actually where just having a sample can be useful. If you know a probability or if you know something about your sample, you can extend it to the whole population. Anyway, here's an example. Let's suppose a survey is conducted to find the most common eye color. All 12th grade students in 5 out of the 7 high schools, I should say, in a city are surveyed, with a number being 2,300 students. So out of the 7 high schools in a city, there's 2,300 students. When they did the survey, they had 1,656 students with brown eyes, 483 with blue eyes, 115 with green eyes, and then just other eye colors, for whatever those could be, 46 other eye colors, right? So use the results to predict how many of the 7,200 college students will have brown eyes. So just to make something really clear here, our initial population in this case is high school students, and they surveyed 5 out of the 7 high schools, so they just took a sample. We could extend it to a different population, of course. The population of college students likely isn't much different than the population of high school students in terms of eye color at very least. So in other words, this would be a valid case to extend. In order to extend, though, we have to do a little bit of math here. Let's figure out our experimental probability that a student would have brown eyes. Well, notice we had 1,656. That is what we're going to consider a successful outcome in this context out of 2,300 students in total. That fraction right there, which I'm not even going to bother simplifying, this is the experimental probability of a student having brown eyes. Now, here's the thing. If this is our experimental probability for our high school students with 2,300 students, we can set this equal to an experimental probability for college students. Notice that on the bottom of our fraction, we had the total number of the high school students surveyed, 2,300. If we are to extrapolate this, in other words, if we're going to carry this forward to another population, we can just change our total number to whatever the total number is in our other population. Our other population is 7,200 college students. So why don't we say that this fraction, this experimental probability, is equal to another probability, so it's the same as another probability except out of a total of 7,200. What that would mean is we can just use this to solve for x, being the top of this fraction, being the number of college students that have brown eyes. Hopefully you remember from a previous chapter in this course, this is just a linear equation. To solve this linear equation, we need to get x by itself. Notice x is being divided by 7,200. To undo a divide, we just multiply by 7,200 on both sides. So if we multiply by 7,200 here, that knocks that out. But what you do to one side of an equation, you have to do to the other. So let me bust out my calculator here. 7,200 times 1,656 divided by 2,300. This gives me, well, actually quite a nice number. X equals 5,184. I say that's a nice number because there's no decimal there or anything. That is how many college students in this city likely have brown eyes. So is this prediction reasonable? Well, this is where you can debate this one way or another. Really, it's a matter of opinion whether this prediction is reasonable. Personally, I would say yes, it is reasonable because the eye colors of high school students and the eye colors of college students likely isn't any different. Not to mention our sample sizes for both of these, 2,300 and 7,200, those are pretty big sample sizes. So in other words, you're pretty much guaranteed a level of accuracy here. Now, reasonable is where you can debate it. Is this number exact? Probably not. No, there probably is more or less of that. We could be off by, a reasonable amount. But I would say it is reasonable because I doubt we're off by really all that much, maybe even off by 100 or 200, which in the grand scheme of things, given this size, probably not a big deal. Anyway, hopefully that makes sense. Basically, what I'm saying is you can use your experimental probability as a fraction to set it equal to another experimental probability with a different population, as long as those populations are similar. And again, when we set up here, when we do this, assumptions about the population are usually made. The assumption in this case was that our high school students and our college students have similar eye colors overall, which is probably a reasonable assumption. Anyway, I'm rambling. So assumptions. With population predictions, assumptions need to be recognized. In the last example, we assumed that the demographics for 12th grade students and college students are similar. We also assumed that the 2 of the 7 high schools that weren't surveyed don't have vastly different eye colors. I forgot to mention that. That is actually a really good point. If that were the case, we would have a biased sample. A biased sample does not represent the population. A biased sample can be caused by things like a small sample size. That wasn't the case in the last example. We had a pretty big sample size. Poor sample selection. Like if you picked schools that for whatever reason would have more students with brown eyes, I don't know what that would be, but that could make a biased sample. Voluntary participation in a survey. So in other words, if you left it open-ended and said, hey, who wants to take part in this survey? That could lead to a biased sample, etc. A good example of voluntary participation in a survey causing a biased sample would be if you're asking people how tall they are, for instance. I hate to say this because it sounds kind of rude, but chances are if there was a survey that you volunteered to go to, the people who'd be signing up for that first would be like, oh, I'm the tallest people. I want to say how tall I am, right? That's what I'm getting at with that, right? So a voluntary participation might not be the best sample when people who want to brag about something might want to go do that sample or survey first. Another good example, like height is one thing, your income, right? If you had a voluntary survey saying how much you make in a year, generally speaking, people who are on the lower income levels probably aren't going to be lining up to do that survey, right? There could be a bias in that, for various reasons. Anyway, moving on. So next up, it's going to seem like a bit of a different focus in this next part here. This is measures of central tendency. That's a really fancy way, central tendency, a very fancy way of saying average. So like it says, these are ways of calculating the average of a set of data. Now, average usually means something called the mean, right? The mean is where you add up all the data and then divide by the number of data items. This gives you the mean average. When we find the average of something, usually that's the method we're doing. For instance, if someone wanted to say, oh, what's the class average on a test? They'd probably use the mean because it's where you add everything up and divide by how many data items there are. The next one is called the median. This one takes a little bit more effort to do. The median is where you order your data from least to greatest. So you line it up from the smallest to the biggest or the least to the greatest, and then you pick the middle number in the list. So you'd actually have to know how many items are in that list so you could calculate where the middle of the list is and go from there. What's kind of interesting is if you have an even number of items in your data set, like for instance, if you had 4 items, like let's say you had like 1, 5, 7, and 8, notice if you have an even number of things, there's 2 middle numbers. With the median, what's kind of cool is when you have 2 middle numbers, you just find the mean of those 2 numbers to find the median. So you sometimes actually have to go back up to this one to find it. So if you were to find the median of this data set, notice it's already ordered from least to greatest. The median would be somewhere between 5 and 7, which is obviously 6. So the median would be 6 in that case. The last measure of central tendency is usually one of the easier ones to find. It's called the mode. The mode is just the number that appears most frequently in the data set. And what's really nice about a mode, well, maybe not really nice, some people might not like this, you can actually have more than one mode. So if there's a number that appears like 5 times and there's another number that appears 5 times, both of those numbers would be your mode. Your mode is kind of, it doesn't get used too often, I'll be honest. I think the number one way as a society that we use mode is when there's an election, right? If there's an election, the most frequently voted for party is the one that generally speaking wins, right? Of course, there's other things that can play into that, but that's a good rule of thumb, right? Anyway, moving on. So here's an example. Suppose Mr. Scott gave a quiz worth 30 marks to 10 students. So it's a quiz that was worth 30 marks and I gave it to 10 students. He marked the first 3 tests and they had scores of 16, 14, and 18. So 16, 14, and 18 out of 30. What was the mean score of those quizzes? Okay, so to find the mean, remember you just add up the number of data items and then divide by the number of them, right? So add up all your data items, divide by how many you had. So in this case, the mean of those quizzes would be 16 plus 14 plus 18, which if you just give me a second, I think I know what that is off the top of my head, but just double check. Plus I have to throw it in the calculator in a second anyway. That is 48, of course. And then, of course, we have to divide that by the number of data items. We have to divide that by 3, and that is 16. So the mean of that data set is 16, just for those 3 quizzes. Now, part B, the following are all the scores. So there's our 16, 14, and 18. There's the rest of the scores on that quiz, right? All 10 of them. Find the mean. Did the original sample, just the first 3 that we did, accurately reflect the population? Why or why not? Okay, so here's where we got a little bit of work to do. We got to add all of these numbers together. I'm going to do that first. So we're going to go 16 plus 14 plus 18 plus 15 plus 22 plus 25 plus another 25 plus 15 plus 28 plus 24. This gives me 202. But then, of course, don't forget when you find the mean, you have to divide by the number of data items. Notice there's 10 data items here, so we have to divide this by 10. And that, of course, is going to give us 20.2. So 20.2 is the mean score on that quiz. So 20.2 out of 30. That was the mean grade that someone got on that quiz. So kind of interesting. Did the original sample accurately reflect the population? Well, obviously it didn't, because the original sample, we had a mean of only 16. But when we did the whole population here, it was 20.2, and that's quite a reasonable amount off, especially when the whole thing was out of 30. So why not? Why wasn't it? Well, it was probably because just having the first 3 quiz marks, that's not really a good reflection of the population, because it was just a random sample and quite a small sample at the same time, right? So it was only 3 out of the 10. That's not a very big sample to work from. Anyway, moving on. Next example, a youth association surveys its 400 members about their preferred activity. There are 100 members in each of the 4 groups. So the 4 groups, of course, are red, blue, green, and yellow. And then they ask them about their preferred activity. So in each of these groups, there's 100 people. Hopefully that makes sense. Question A here is, what is the theoretical probability of any group member choosing swimming? Notice they could choose swimming, climbing, movies, or bowling. What's the theoretical probability of any group member choosing swimming? Well, in this case, because we're just given 4 different options here, you have to assume that all the options are more or less even. Yes, obviously, if you look at the data, they're not. But in theory, the theoretical probability of a group member choosing swimming should just be 1 out of 4 options. 1 option is swimming. They had 4 options in total. What assumptions did you make? Well, the assumptions we make are that all activities are equally popular, right? We don't really have anything else to go by when we make a theoretical probability. We have to make the assumption that all activities are equally popular here to say that the chance of someone choosing swimming is 1 out of 4. Now, based off the survey, what is the experimental probability of choosing swimming? Now, this is where it's kind of set up weird. We had 4 different groups with 100 people in each group. Since we're just asking the experimental probability of anyone here choosing swimming, we have to realize that the total number of people surveyed are 400, not the 100 in each group, just 400. Really, these groups aren't mattering for any of this. So in terms of choosing swimming, we have to look at all of the people that chose swimming. So we should add all of those numbers together as our successful, quote unquote, to go up on the top here. So 14 plus 11 plus 27 plus 13. That gives us 65 people who chose swimming in general. So the experimental probability of choosing swimming is 65 out of 400. You could probably simplify that fraction down. I know you could divide by 5, and I think that's probably all you can do here. So if you divide both the top and the bottom by 5, that gives us 13 out of 80. So 13 out of 80 is the experimental probability of someone choosing swimming. Just by the way, it just kind of dawned on me right now, some people might be wondering, with probability, I've always been expressing them as a fraction where it's successful out of total. You might be saying, hey, can't you just express this as a percentage as well? People, when they say probability, they often say, oh, what's the % chance of something happening? Yeah, you can actually put this as a percentage. To do it as a percentage, you just divide this fraction and then times by 100. So if you're wondering as a number, just divide that fraction times by 100. That's going to be 16.25%. So that would be the percentage chance of someone choosing swimming experimentally, at least, just from this experiment that they did. If you looked at the theoretical probability, it's 1 out of 4, which hopefully you can see is 25%, but it is what it is, right? Anyway, next example. I think we have a few more examples. Let me just go forward real quick. 2 more examples. Here we go. So a light bulb factory samples light bulbs as they come off the assembly line. A random sample of 20 bulbs finds 1 to be defective. If they make 1,400 bulbs in an hour, the manager predicts that 70 bulbs will be defective. What assumptions did they make? Well, here we are. So first things first, we should just check their math on this one. Their random sample, which is an experimental probability, found 1 defective out of 20. Now, I know it's going to be a little weird, but we're going to call a defective bulb a successful one in this case, just for the purpose of calculating experimental probability. So the experimental probability of finding a defective bulb was 1 out of 20. We could expand this to the entire population, which is 1,400 bulbs in an hour, so 1,400. X would be the number of defective bulbs that are coming out of this. So to solve for this, we just multiply by 1,400 on both sides. 1,400 times 1 divided by 20 gives us X equals 70. Okay, so first things first, their math checks out. When this manager said, oh yeah, 70 bulbs will be defective, the math checks out. Now the question says, what assumptions did they make? I guess the main assumption that you could say here, I won't bother writing them down, you can just listen to me mention it. The main assumption that they made here was probably that these defective bulbs are happening at a constant rate of 1 out of 20. They're also assuming that there's not more defective bulbs, and they didn't just get lucky by pulling one defective 1 out of 20. Conversely, they're also thinking that, maybe they didn't just get like unlucky, or I'm not sure how to put it. Maybe this was the only defective bulb and they just so happened to have pulled it. So basically the bottom line is the main assumption they're making is that these bulbs are defective at a constant rate of 1 out of 20. So anyway, moving on. Last question here. A toothpick factory samples every 100th toothpick for damages and finds a 0.17% probability of damage. Ooh, it's a good thing I mentioned percentage earlier, because there it is. If 2.4 million toothpicks are made daily, predict how many will be defective. What assumptions did you make? Okay, so just remember a percentage. So like 1%, for instance, is 1 out of 100. So if you had 4%, for instance, that would be 4 out of 100. The reason I'm setting this up with these random numbers here is we have 0.17%, which would be 0.17 out of 100. Just make sure we're all clear, because you do need to use fractions to get this to work, or at least it makes it easier. Anyway, this is our percentage of damage. So 0.17 are defective out of 100. We want to see how many will be defective if we're doing some math on this one. Notice there's 2.4 million toothpicks being made daily. Those are going to be our total number of toothpicks. 2.4 million would be that number right there. We want to find how many are defective, so I'll put that as our X on the top. To solve for this, we just need to multiply by 2.4 million on both sides. So 2.4 million multiplied by 0.17 and then divided by 100. You might want to type this in a calculator just to make sure that you got this. You need to pause, go for it. The answer I got is 4,080. 4,080, right? That would be the number of defective toothpicks that are made daily, assuming that we have a 0.17% probability of damage. So again, that comes into our assumptions bit. The assumptions that we make here are that this probability is even for the entire set of toothpicks being made. We're not assuming that we got lucky or unlucky with this probability that found when we did a sample of 1 out of every 100 toothpicks. But yeah, we're also assuming that these damages don't happen in certain intervals, right? So we're picking every 100th toothpick. What if the machine making the toothpick, like all of a sudden runs into a defect every like 20th toothpick or so, and then rolls a chance to see if it messes something up? I don't know. I'm just kind of rambling on this one. Basically, the main assumption on all these questions are that we're assuming that our probability of damage stays consistent and even over the entire population of toothpicks being made. Anyway, enough is enough there for practice. I want you guys working on these questions, page 436, questions 8 to 14. These ones are from a previous day. If you haven't finished them already, make sure you're getting them done. And if you have any questions, please let me know.